Right, so let's welcome Sri Raghu, who will tell us more about density waves in the Kagome lattice. So Sri, it's over to you.
Thank you. Thanks, Yasir, for the invitation to come here. And thanks all of you for coming. It's great to see some old friends and many of you. And I also always love coming back here. This is a wonderful world-class facilities. So yeah, thanks for having me. It's great to be here. All right, I'm going to tell you about some work that I did on the Kagome lattice in collaboration with Yiming Wu. Oh, okay. Yiming Wu, who's shown on the left here, who's a postdoc at Stanford, a very talented postdoc, and one of the co-organizers, a very intense-looking Ronny Thomale. Okay. So before I start what we tell you what we actually did, let me give you some motivation. As you all know, there's a class of materials on the Kagome lattice, like cesium, vanadium-3, antimony-5, which host an interesting set of density wave orders. Okay? So what's interesting about density waves in this system? So the experimental results that I show you up here are observation of Bragg peaks and their magnetic field dependence. So there are some Bragg peaks observed in the Brillouin zone, indicating broken translational symmetry. And if you apply a magnetic field, this is 2 Tesla up and 2 Tesla down, the Bragg peaks shift a little bit. Although I don't particularly see a difference between zero field and finite field. Leaving that aside, the claim is that the Bragg peaks have a sort of associated chirality that flips, indicating some kind of time reversal symmetry breaking. Okay, so charge density waves that might break time reversal symmetry is the observation. Now, in addition to that, the magnetoresistance, the Hall resistivity, exhibits pronounced nonlinearities at zero magnetic fields associated, or as the papers say, concurrently with the charge density wave order. This has been called an anomalous Hall effect. We'll come back to that. I don't think that's a correct way nomenclature, but nonetheless, there is some interesting Hall response suggestive, again, of time reversal symmetry breaking. Okay? So early on, based on these experimental measurements, several people came up with theoretical ideas that were basically recasted versions of older ideas that were proposed in the context of the Couperate pseudo-gaps, so flux states and d-density wave type orders. And so an example of these pictures are from the paper by Leon Valence. There's some sort of orbital current orders. They break translation symmetry and they break time reversal symmetry. This has been suggested. You can have a system of orbital currents that have the threefold rotational symmetry, 120-degree rotations, as shown here, or you can have orbital currents that break the 120-degree rotations down to some, so twofold rotations remaining only. And many people have worked on this, and I haven't cited all of them. Sorry about that. But some papers that early on suggested similar things were by Rahul Nankishore, and an extensive classification was by Jiangping Hu, who is giving a talk later this week. The other interesting thing in these materials were exotic, or suggestive of exotic superconducting behaviors. So in this work back in 2021, the scanning tunneling STM measurements Fourier transformed found some Bragg peaks as suggestive of the CDW, but as you went to lower temperatures, there were new Bragg peaks shown in these pink colors, which are approximately half. You can see that the distance between the green and the blue is about approximately half. This Bragg peak is approximately half the CDW Bragg peak. So that's suggestive of something interesting, and the authors themselves commented something known as a pair density wave superconductivity. So for those of you who may not know what this is, as you know, in superconductivity usually involves Cooper pairs with zero center of mass momentum. A pair density wave has finite center of mass momentum. It's basically a modulated superconducting order parameter. So if you measure the gaps in STM, you would see gaps that vary in space in some cosine-like form. From this variation, you can extract a wave vector Q. And you know, from Ginzburg-Landau type reasoning, not very sophisticated, you can find that you can show easily that the pair density wave Q is exactly 1/2 the charge density wave vector. That's because there's a coupling in the Ginzburg-Landau free energy between the charge density at some wave vector Q, CdW, and the pair density wave. And so this has to be translationally invariant and gauge invariant. So you can see that that requires that the pair density wave momenta, or ordering wave vector, must be half the CdW. By contrast, if you just had a boring coexistence phase of just a uniform superconductor and a charge density wave, there would be an induced moment to the superconducting order parameter at the same wave vector as the charge density wave. So this difference is important, and the fact that they observed a different Q in the gap maps at low temperatures suggests that it might be a pair density wave. Okay, furthermore, there's pronounced one of very interesting superconducting fluctuation spectrum. So in the resistive state, above 1.5 Kelvin or so, there have been magnetoresistance oscillations. And depending on the geometry, so for instance, in this geometry, you see charge 2e oscillations near the superconducting state where the resistivity vanishes. But also above that, where the resistivity is finite, you see charge 4e oscillations and even charge 6e oscillations. So that's unusual and can naturally be accounted for if we had a pair density wave order, because out of a pair density wave at wave vector Q, you can construct a charge 4e superconducting state, which is at Q equals 0, right? By taking a pair density wave at Q and a pair density wave at minus Q, and each of these are 2e, and so this is a charge 4e superconductor. The fact that it has uniform momentum enhances the fluctuations, at least. It's likely that you can have fluctuations from this. Furthermore, you can have charge 6e because of the triangular geometry. Since the Q's add up to 0, you could form a 6e condensate, which can also have, can also exist in the fluctuation spectrum. The fact that these have, there's pronounced magnetoresistance oscillations is extremely interesting. Okay, so that's the backdrop for what I'm going to tell you. Any questions? I'm actually hoping this is more like a discussion rather than a formal talk where I talk at you. Any questions so far? Please feel free to interrupt. Yes, please.
Sorry, at the beginning, when you talked about the shift of the charge density waves being maybe by experiment, I'm not sure.
It was STM Fourier transformed.
Okay.
Yeah.
So the shift in the intent, were you talking about a shift in the intensities or a shift in the wave vectors or what?
It was a shift in the intensities. So you're referring to this up here, right? Is that what you're referring to?
Yes,
Yeah.
exactly. Yeah.
So you can see that the intensity here is less than the intensity at this peak.
Right.
Okay, so if you draw an arrow from the less intense to the more intense Bragg peak, there's an arrow going this way and an arrow going this way. So like this, right?
Right.
But now in the opposite field, the arrows flip. So that's what led the experimentalists to say that there's some kind of chirality associated
I see.
with it.
Okay. Thank you.
Yeah. But it's important to note that the zero field doesn't look all that different. So
Yeah. Right.
yeah, okay. All right. Other questions? Okay. So here's a simple theoretical story that I want to tell you. I want to be careful because the experiments are far more interesting than the theoretical simplicity that I wish to convey you right now. So this is not a theory of these interesting materials, but what it is an analysis of what happens to electrons in the presence of repulsive interactions when they're on a Kagome lattice and the filling happens to be near this Van Hove singularity that you heard in the previous talk. Okay, so since we're in 2 dimensions, the density of states diverges logarithmically near a Van Hove singularity. To a reasonable approximation, you can ignore all of the Fermi surface except the points near the Van Hove singularity, the so-called patches near the mid faces of the zones, okay, where the Van Hoves occur. And then you construct a scaling theory of those patches. And this was pioneered by Heinz Schultz and also by Igor Dzhelezhinsky in the early days of the cuprates. And it falls under the name of, so we borrow a name from 1D electron gas physics, something called geology. So you have some Hamiltonian, which has kinetic energy of the Van Hove patches of the electrons, and a bunch of interactions which can be represented as forward scattering, back scattering, like you have in the 1D electron gas with some coupling constants G. okay? And this has been called geology. And because everything, the density of states diverges logarithmically, the renormalization group flow of this involves log squared divergences, which can be treated in a simple way just by looking at the leading log squared instabilities. And you get an RG equation of some form like this. So from the ith G has some running in this form, marginal couplings, and this gamma is some RG matrix. When you diagonalize, you get the scaling fields, okay? So when you do this, you find some results. I don't want to bore you with technical details, but so there's a bunch of G's, and as you change the RG time, the interactions flow, and when you diagonalize this RG matrix, some appropriate linear combination of those G's, which I call scaling fields, will indicate different types of broken symmetry tendencies, some growing susceptibilities. So if you had, in this instance, we find that the leading instability is some kind of spin density wave. But don't take this very seriously because it neglects a very important effect, and that's one of the key points of my talk. It neglects this notion that Ronny Thomale had coined called sublattice interference. Actually, I remember when he was at Stanford when he came up with this, and I didn't appreciate the importance of it then, but now I do. And the idea is the following. So the previous speaker already talked about this. So you have lattice electrons on the Kagome lattice, and when you go to the band basis, there are some overlaps. There's some, the rotation, the diagonalization for going into the band basis involves some wave function in k-space, some amplitudes in k-space. And it turns out that if you look at the sublattices, A, B, and C, the Kagome has 3 sublattices, the support of the wave functions of, say, the A sublattice is only on one Van Hove singularity, and B is on the other one, and the C is on the other one, okay? There's no admixture, and so that's why this was, as you heard in the previous talk, something called a pure Van Hove singularity. Okay, so the first thing theorists would do is study the Hubbard model in the presence of this lattice, but now including these effects of sublattice interference. So you write down the Hubbard interaction, and then starting from the microscopic Hubbard U, you derive what these G's are. And you find that the role of the sublattice interference is important, because what you find is that all of the G's shown here are 0 except one, G4. So this is a very simple exercise in now computing the RG flow. You find that the coupling G4 just weakens under the RG flow. So whereas previously I showed you all this very rich interplay of different orders, now the system is trivial, okay? So you find that everything just flows to weak coupling, to non-interacting electrons, and so the conclusion is that the Hubbard model is trivial, a phrase you don't hear very often. Yeah? Is there an enhanced symmetry? The only symmetry that's occurring is the threefold symmetry, but also the fact that when you go from, it's invoking the fact that, because the Hubbard model involves all momentum states, all momenta, right, when you Fourier transform. But the sublattice interference considerably weakens the backscattering aspects. So that's just it's not a real symmetry, it's just, it's still present.
It's not enhanced to something more.
No, it's not. No. It's only C3. Okay, so free fermions. So because we don't want to work with free fermions, nothing can happen with free fermions, we say that the Hubbard model is useless now. So let's go to the next thing, which is you add some nearest neighbor type interactions. Okay, so now, because previously there are 3 Van Hove patches, the Hubbard model form factors are momentum independent, right? It's just on-site interactions. But now when you have nearest neighbor, there's some momentum dependence, so there's a distinction between a Van Hove point here and its inversion symmetric relation. So K and minus K are different. So therefore now we have to have a 6-patch theory. So there's more, it's no longer a back of the envelope calculation, but again, I don't want to bore you with technical details. You can do this, and you find that while the Hubbard model interaction U runs weak with RG time, the nearest neighbor interaction V runs strong with interactions, in RG time. Okay, so, and the other thing is that the scaling fields that you obtain from diagonalizing this RG matrix remains very simple, that namely there's one G that gives rise to U and there's one G that gives rise to V, and they don't mix under the RG. So there's a one-to-one mapping between the microscopic couplings and the emergent low energy couplings in the RG flow. That's just a technical detail. That's not true generically. So in the weak coupling limit, what you do is you say, well, look at the leading susceptibility when it's most important, and you see what the biggest susceptibility is, and that enables you to deduce what the most leading instability is. So in the limit where these interactions, although they run strong, the RG eventually will break down. That's what this gray region is. You should never trust a one-loop calculation far out there. But if you start somewhere here where the V is bigger than the U, and you just do a one-loop calculation of the susceptibilities, you find that the weak coupling instability that's dominant is something like a complex charge density wave, okay? And also a complex spin density wave. So unfortunately, yeah, it's a property under reflection under K to minus K. So actually what we find is a CDW which is odd under reflection. That's all it is. But if you want to know the real space pattern, like I showed you in the beginning of the talk based on other people's works, we can't do that here in the simple patch model because the order parameter for such density waves are a sum over all k with some f of k. But if you only have 6 k's, you can't uniquely determine that. So we can't uniquely determine what the orbital currents are. We know that they're imaginary, they break time reversal, but we don't know exactly the real space lattice pattern. For that, you'll need to do some kind of mean field analysis, something like that. Okay, so this is what happens without this phenomenon of sublattice interference, and this is what happens with sublattice interference. So this is why I never appreciated the importance until we did this. It obviously has physics in it. It has physical consequences. It's not just some single particle curiosity. Okay, so now if you go away from the weak coupling limit, you don't have any theoretical control, but that doesn't stop us from saying things. So we will just say something, and you simply analyze the susceptibility, and we deduce, you can compute analytically the particle susceptibility shown in blue, the particle hole susceptibility shown in red. Just for the sake of simplicity, we can remove unphysical nesting effects and show that there isn't all that big a difference. But the upshot of all this is that when the couplings are of order 1, instead of these imaginary density waves, you get what looks like a pair density wave. So the superconducting state occurs not at uniform q equals 0, but at finite q. Okay? So now I want to just give you a simple explanation for why this happens. So we said that the Hubbard model is weak and the nearest neighbor interaction gets strong. In that regime, you get a pair density wave. Why is that? So here's a simple toy model, like a spherical cow-like model for this, okay? Imagine you had a BCS model with repulsive couplings between pairs. I think Brian has worked on something like this as well. But now the repulsion enables you to only operate a distance r naught away. So there's no repulsion at short distances, no repulsion at large distances, but just a repulsion at one distance r naught. Okay, so this is like a caricature of having no Hubbard U, a nearest neighbor V, that's positive, and then all other interactions 0. So the thing about this is now when you Fourier transform this in position, going from position space to momentum space, you see that although at q equals 0 it's positive, that means it's still repulsive, at finite q there could be attraction. And so if you crank up the coupling sufficiently high, you could get a situation where there's no longer a BCS-like instability at finite q, but if you make the coupling big enough, you can see that there could be a finite q order. And that's essentially what we found. Okay, so I'm done with the theoretical part of my talk. Now I want to make contact with what, if any of this, has in connection to the experiments. Okay, are there any questions thus far? Okay, so let's now, based on what I've told you, see if there's any connection to experiments. Well, here I'm less optimistic. So the theory is utterly simple. I'm confident about it, but I don't know if it's relevant to experiment. Again, we're not analyzing anything about these Kagome metals, but we're simply studying these patches. The patches are a grotesque approximation for real physics, but nonetheless, that's what we found. We found that there's complex charge density waves at weak coupling. We found pair density waves. I didn't say that, but the order parameter lives on bonds at intermediate coupling, and that the sublattice interference plays a crucial role. So these could account for some of the experimental observations. There was namely broken time reversal symmetry and pair density wave states. But it's important, I think, for us to see if there's dumber or more boring possibilities to account for the data. I just want to give you some very boring possibilities to account for everything that's been noted. So I talked about the Hall resistance data, the so-called anomalous Hall effect. Now, that was said maybe there's some exotic thing going on with broken time reversal, but here's a very boring possibility that gives you more or less the same thing. You measure the Hall resistance, so now I'm putting on my hat as a phenomenologist, not as a theoretician, okay? So you measure the Hall resistance, it's B over NEC. If you're near a CDW ordering, there's a new pocket that forms. The pocket, if it's small, N is small, you can get a huge RXY. Now, if N furthermore depends on temperature, as it clearly does in this inset here, you can have a very nonlinear Hall response, which might look anomalous, but it's not because it vanishes at zero field. So I think this is not an anomalous Hall effect, and calling it that is incorrect. Furthermore, in an important recent experiment by my colleague Aaron Kapitolnik, the Kerr effect in the neighborhood of this CDW was studied, and it was clearly noted in careful experimental studies that there is no Kerr effect. And I should say that the Kerr rotation, when light shines at normal incidence, the requirement for a non-zero Kerr rotation is the same thing as a requirement for the anomalous Hall effect. Namely, you need to break time reversal, you need to break vertical mirror symmetries, and it's at Q equals 0. And absence of one, I think, implies absence of the other bisymmetries. So if you just have a boring CDW with a pocket, you can account for these data. What about superconductivity? It's encouraging that the Bragg peaks at half the CDW wave vector have been observed, and that's indicative of a pair density wave. But as far as I know, please correct me if I'm wrong, these experiments have not been reproduced, and we don't know what the temperature dependence is of the pair density wave peaks. We don't know what the condensate fraction of the pair density waves is from the gap maps. You can see if the gaps oscillate very much, that's a big condensate fraction. We don't know such information. And also, this very interesting and intriguing 4E and 6E fluctuations haven't been reproduced. So there's a lot of, I think for me at least, I want to wait and hold on and see what's coming up before I venture and say that the theory we did is relevant or not. Other things that worry me, but quite interesting, is that the role of disorder here. Namely that the superconducting transition temperature doesn't seem to change with disorder. This, under most circumstances, suggests the simplest possibility that this is not some unconventional superconductor, it's just S wave. And certainly the pair density wave is going to be devastated by any impurities. And the fact that there's nothing going on here suggests that maybe the pair density wave isn't all that important. Now, I should see, however, I think Brian is talking about impurity effects on this, and so the sublattice interference might have interesting consequences. So more to be seen. So that's the summary of my talk. We did some theory, we found some results. I have no clue whether it's relevant to experiment, because on the one hand, you have what can be explained with boring, simple ways, Occam's razor, but on the other hand, there's tantalizing data in the fluctuation spectrum and very interesting effects. So I don't know which side of the coin these systems lie on. So thank you for your attention.
Questions?
Well, thanks very much. Very interesting. Just a comment that supporting the Kerr rotation data, there's been a lot of effort, a lot of MUSR effort trying to look for time reversal symmetry breaking, and I think that continues to be inconclusive or null.
Yeah. Okay.
So, Sri, just a very naive question.
Yeah.
Your T breaking, time reversal symmetry breaking, this is just like having these current loops.
Yes.
So in relation to Shubhra's question, can I think of this as some sort of Ashkin-Teller type model in some dissipative background, like Aji and Chandravarma did?
Maybe. I'm
then
not sure.
the question makes actual sense. I mean, you can get emergent symmetries there, right?
Yeah, but I think there you need, you mean some composite order parameters?
Yes. But coupled to a dissipative environment. And then you can have enlarged.
Yeah, I mean, I don't know if that's been looked at. We certainly didn't look at it, but it might be interesting to think about, yeah. I don't know if that's going to change any of the story either, yeah.
Hi, thank you for the nice talk, really cool. A bit related with the previous questions, there is a work from Philip Moe group that they claim that the time reversal symmetry breaking actually comes from the strain on the sample, where they measure non-strained samples and they don't see time reversal symmetry breaking. And when they strain the sample, they see that, and magnetic field has the same effect on it. So my question would be, could you construct some kind of an idea of getting out of pure type Van Hoven singularity, applying strain and recovering all these PDW phases and also all the physics that you came out here?
So, okay, so the time reversal breaking doesn't require the superconductivity. You know, you can do this with just the density waves, right? So I think that's what you meant, right?
Yeah.
I mean, at the level of Ginsburg-Landau theory, it's a trivial thing to do, you know. Strain can couple in a way, and if there's an order parameter that has the right symmetries, it can respond to strain and result in a Kerr-like response, you know, some reflection symmetry breaking. So I'm not sure if that's what you had in mind, but sorry, go ahead.
No.
Yeah.
Good. Can go ahead.
But I don't know of any in theoretical work.
Yeah, there is some theoretical work on this, actually from Rafael Fernandez. But I was just going to comment, actually, that you can try doing, this is actually a little bit puzzling. So if you want to, just in Landau theory, explain both of the Philip-Moll experiments with strain and the magnetic chiral anisotropy, if you want to explain both these experiments just with additional charge density waves, you have to posit the existence of 4 distinct charge density wave orders that appear that all break symmetries in different ways. So it's actually it's kind of puzzling how to explain all of his experiments just with resort to charge density wave order only.
I should also say that when you apply strain, you also have inhomogeneous strain. And inhomogeneous strain acts in many ways like random magnetic fields, actually, to some of these order parameters. So, you know, I don't know if Raphael took that into account, and that's an important effect to take into account.
Well, strain shouldn't break time reversal symmetry.
It doesn't.
So
but
there are symmetry constraints on.
No. But if the density wave order breaks time reversal symmetry and you have strain impurities, then there could be effects.
Yeah, that's fine.
If at finite q you have, you know, a density wave at finite q, some orbital currents, you won't see any response to, say, the Kerr effect. But with strain impurities, you could.
Yeah, actually, this is, I'm not sure if it's a standalone paper, but this symmetry analysis is in the supplementary material of an experiment by Vidya Madhava that Rafael Fernandez.
Yeah.
Actually, I think Turan was also on that.
Yes, I will be talking about that in this afternoon.
Yeah.
There are different things people mean by time reversal breaking. So if you mean the emergence of a ferromagnetic pole specifically, so that corresponds to piezomagnetism. That's fairly easy to get into the phenomenon.
Yeah.
So perhaps we can talk after.
Yeah. Just the comment I was making initially is that it's straightforward to get piezomagnetism. That's what they did. But it's kind of puzzling to get both piezomagnetism and chiral anisotropy, which is the other Philip-Moll experiment.
Thank you.
Thank you.
Just a short question about your model. So you have your patch model, and you restrict it to the endpoints, right? The Van Hoek points.
Yeah.
And the cancellation of the sublattice interference removes most of the physics, basically.
Right.
And then you go to nearest neighbor.
Yeah.
But why don't you go to other K points? I mean, the cancellation is just perfect at those particular points, right? So do you know, does do you know anything about consequences of including other patches or nearby K points or something already for the U?
So even at U, even away from the Van Hove points in the geometry, let me show you the, where is it? Okay. So yeah, here, you don't need to be too close to the Van Hove. You can be in this red region, for instance. There's still these kinematic blocking effects.
Yeah.
But they're hard to deal with when you have both the Van Hoves and the subleading. So there's absolutely no theory of instabilities of Van Hove singularities that takes into account the subleading parts of the Fermi surface, actually. Yeah, it's a fundamental open problem. Yeah.
Shri, for your 6-patch model, what is the pair density wave Bragg peak you find? Is it
It's at the M point. Yeah, so that's so it's basically the zone corner itself. Yeah. I didn't mention that. I think there's been some experimental evidence for such order recently. I remember seeing some things in the archive, which I didn't present here, but I can dig it up if we want. If you want, we can chat about it.
Any further questions or comments? If not, let's thank Sri again for a very nice talk.
Thank you.